Okay, 4, section 3.4, linear inequalities. Now, the difference is instead of saying equals, we have an inequality. So we are saying it can be equal, but it can also be greater than or less than. And it can be greater than or less than and not equal to. So what happens in that case, and we'll get to this, is basically we graph a line on points that we find as though it was set equal to. We solve for our ordered pairs the same way we solve when it's equal. But once we plot those points, then we start thinking along the lines of, is it greater than or less than, or greater than equal to, less than equal to. So linear equality in two variables. Boundary line on graph is solid if it is equal, but broken if it's greater than or less than. So in this case, this one includes an equal sign, example 1. So it's a solid line because it does include those points. Remember, we solve for the points. Let's take this one for example. If I want to know the y-intercept, I just plug in 0 for x, y equals 4 for my data point. For the point, I assume I treat it like it's equal. And then I list as many points as I want. I could find as many of them as possible to make a good line. That's when I transition to thinking greater than, less than. And in this case, it says equal, so it does include that line. Think about it like a boundary. In most sports, if that ball touches the line, it's completely out. But if there were a case where the line included the inbounds and it had to be totally outside of the line, well, then in that case, it would be included. So right now, we're saying it's equal to, it includes those points. But if it's greater than or less than, like this, means now it doesn't include those points. It's everything less than that. Okay, so you can look at my little notes here. What I've written here, boy, that's a crappy shading process. Pause it if you have to. I said make sure to check the page 245 how to. That helps us better understand how to graph linear inequalities. The hint that I will explain a little further is once you graph your line and you have to figure out where to shade, super easy, super simple concept. Pick a point that's not on the line and plug it into the equation. If it's true, shade that area. If it's false, shade away from it. So in this case, if you plug, I always plug the origin in if it's not included in the line. Right here, 0, 0, that's nowhere near the line, so I can use it. It's the easiest one to plug in to check. I plug 0, 0 in, 0 less than or equal to 4, that's true. 0 is less than 4. So I shaded where my 0, 0 was. I'll do that again in the examples. So let me do a couple. I drew up some graphs as well. So for section 3.4, problem set 3.4, I said let's work out number 9. Number 9 says graph the solution set for 2x plus y less than 5. So again, what I'm going to do is treat this just like what we already did in 3.1 through 3.3. If I want to find out where my line falls, I need to plot my points. To find my points, I treat this just like an equals. So to think point-wise, we could think equals. So if I make x 0, that means y equals 5. So I'll say there's 1 point. So I have a point. Now, if I make y 0, I see that I'm going to have a fraction. I don't really want a fraction. So right now what I'm going to do is I'm going to stick with x, but I'm going to see what happens if I make x a negative 2. And again, I'm doing this just so that you can see we're just choosing some points. If I make x a negative 2, then I would have -4 plus y equals 5, and I'm going to add 4 and get 9. Now, what I don't want to do is graph a 9. So I'm going to choose a +2 and see what happens then. We can choose as many as we want. That's why I'm going through this to show you how I also set it equal to 0 to avoid confusion. So now I have 4 plus y equals 5, and I'm going to subtract 4. Well, y is 1. Okay, I can plot that, and I can plot that, and there we go, finish my parenthesis out. I could do another one just to see what happens, because it'd be good to have 3 points when I'm not that far apart. If I go up only one more with x and make it 6, or 3, make the x 3, then I have 6 plus y equals 5. You can kind of see what's happening. Now y is going to be a -1 because I went up 2 more. So I went from 1 to -1. So if I were to make it 3, I actually get a -1 then. I have quite a bit to graph. I have 3 good lines. I have, or data points. I found 4 data points. I don't want to graph a 9. So I'm going to choose this one because I didn't realize this is goofy graphing paper, so I ran out of room up there. So I know that I have a point, get it on here. I have one ordered pair that's 0, 5. So I can plot that there. That one I'm skipping because I don't have a 9. I don't want to draw that big of a graph. Then I have a 2 and a 1. This is a steep line we can see going down this way. And then I have a 3 and a -1. So here's my line. Now, before I connect it, this is the point. Finding the pairs, the ordered pairs, I can treat this as equals. Before I draw my line, I have to revert back to what it tells me. In this case, in number 9 says less than. That means I am actually going to have a slotted line, a broken line. Sometimes I'll say slotted, sometimes I'll say broken. I try to say broken because that's the route the book takes. Okay, that's part of it. Now that I have the line drawn correctly, slotted meaning it doesn't include it, I have to go back, and now some people argue and say, well, it says less than, so can't you just highlight or shade underneath it? However, there are times when we're dividing by a negative or multiplying by a negative, so it's a little tricky to always go by what this says. The 100% accurate route is to take a point that's not on the line. Choose any point that's not on this line. This point's not on the line. This one's 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 not. I can use any of these points, or I could use points out here. Anything not on the line. My go-to, obviously, is always the origin. If the line does not pass through the origin, I choose it because it's a 0 and a 0. So what happens is I check. If I choose the origin and plug it into the original equation, my original equation, 2x plus y less than 5, I'm saying, okay, what happens with the origin, 0, 0? If I plug that in, I have 0 plus 0 is less than 5. Now, that is a true statement. 0 is less than 5. True. If it's true, I shade that point. So that means this is the part I shade. Okay, done with number 9. We'll do a couple more. So number 21. Number 21 says graph this inequality. X greater than or equal to 3. So again, this came up in one of the earlier sections. Don't let it throw you off. Those are super easy questions. People get confused and overanalyze them. because there's no equation. There's not an equation solved. There is nothing to solve. That makes it easy. Go that route. Think, cool, I don't have to do any work with this one. So it says x greater than or equal to 3. Well, all I care about is x when it is 1, 2, 3. Right there is x3. Then I look and is it equal to? Yeah. So it's a solid line. So I draw my solid line at x3. And then this one, I don't have to test anything. This is literally saying x greater than or equal to 3. So any x that's 3 or bigger. And I'm done. That's how I graph these. The solid line, if it's got the little line underneath saying equal. And then in this case, I only have one thing to worry about. All x is bigger than 3. Now I'll do one more. Number 31. Number 31. Oh, you're welcome for doing this one for you. This is a nasty one. I have found my students hate fractions. Fractions are the #1 most hated aspect of mathematics. Negatives are close behind. But what I've found in the classes up through intermediate algebra, fractions are what people hate the most. Make them go away. When you have any equation or inequality, any equation or inequality that has a fraction, you can make the fraction go away. You simply multiply by the LCD. The least common denominator here is 6 because 3 and 2 both go into 6. So I'm going to multiply the whole entire thing by 6. When I do, I can break each one of these down, but I want you to get used to just thinking of it as one number times all of these. So the way you can think in your head of doing these is 3 goes into 6 2 times. 2 times x is 2x. 2 goes into 6 3 times. 3 times y is 3y. And I can't forget the 1. The most missed-ish step, I should say, the most common wrong answer is people forget to multiply that last one, the number on the other side of the equal or inequality. So you have to multiply every single term you have by the LCD in order to get the fractions to go away. So if a third plus a half is greater than 1, 2 plus 3 is greater than 6. Basically, that's what we're saying here. Okay, now that I have this, you do not have to worry about slope-intercept form, getting y by itself. When you are just plotting a line, your only concern is choosing points. You can do the table method if you like. Some people like the table method, x and y. I'm going to choose 0 for x first. When I do, I zero that out. 3y greater than 6, I divide by 3, y is greater than 2. Well, when they're set up like this, well, now I'm going to throw a 0 in over here. I'm going to find both my intercepts. So when I zero out y, I'm left with 2x greater than 6. And I divide 6 by 2, and I get x equal to 3. I have both my intercepts. I don't need anything else. I'm just going to graph it using those two. You could go ahead and go negative route for x if you want, because you got a 3. You could try a negative and see what happens, but then it starts getting more tricky with, you got to make sure the fractions go away to make it easier. So once I get this, and this is the last one we're going to do, I have my graph ready here. I have a 0, 2. There's my y-intercept. And then I have a 3, 0. There's my x-intercept. Now, looking back at this, I'll put it right here so that we have, oh, I should have folded it a little more. All right, there we're looking at the system right here, and we see a greater than. So it doesn't include, it's not equal. So I have a broken line. So I'm going to make a broken line right here and make it as clean and straight as possible, which isn't always that easy. So greater than, I have my slotted line. Now what I'm going to do is my origin is open again. Every time that's open, use that to test. So I'm going to test using 0, 0, using the origin. My cat just got sick. I tried to talk loud and cover that up. Yuck. All right, maybe I'll leave it and the wife will clean it up. So use the origin 0, 0 and test. When you do, 0 times anything is 0, and I have 0 greater than 6. 0 is not greater than 6. So that's a case of false. When it's false, I'll write shade away, kind of like Swing Away. Any Signs fans out there? Pretty good movie. Swing Away, Meryl. So shade away. So you got 0, 0 origin. When I plug that in, it's a false statement. I don't include that. It's not included. Everything else is. So I shade on this side. So my test point, if my test point leads to a true statement, I shade it like this. If my test point leads to a false statement, I shade away from it. All right, that was section 3.4. So hopefully that's smooth sailing for you. Let me get out of this and we will be back for 3.5.